Okay, welcome. We're here with Eckhard Elsen, who is Director of Research and Computing at CERN in Switzerland. This morning he gave a keynote here at the EGI conference in Amsterdam. So welcome.
Yeah, thank you for welcoming me here at EGI and allowing me to introduce some of the program at CERN. Our business at CERN is of course to do physics, fundamental physics, particle physics, in which we foremost collide protons on protons at very high energies, and we look at the products of the collisions. Now these collisions are registered in very huge detectors which record all the details of this collision and produce enormous data streams and volumes of data rates and data streams which we then have to analyze. The principle of operation at the CERN Hadron Collider is to have the protons collide, register the data, and then the physics group sit down and sieve through the data samples to understand what is in them. Now, since we are looking for very rare collisions and the collision is a probabilistic process, we have to sieve through a lot of data to really find the new physics which we are looking for in the end. An example is the Higgs discovery that happened, was announced 4 years ago now, which was, of course, the duel after a long search for that particle when it was finally found. It led to the Nobel Prize to Higgs. Now we would like to repeat such a monumental discovery again, which is why we increase the interaction rate, the strength of the collision. We call it luminosity. What we want to do over the next 6 years or so to gain 1 order of magnitude in the interaction rate, and then we are looking forward into 2035 to gain another order of magnitude. The data rate at these times are already among the biggest created artificially in the world. Now, if you add in a factor of 100, you can understand that we will have one of the biggest computing needs whatsoever. The technology we are using since 15 years or so is the worldwide LHC computing grid, which has been performing well. It consists of a federated network of computers which have fast links in between them so that we can analyze the data, be it in the US, here in Europe, or in Asia. The next step of this evolution is a somewhat more generalized approach, which typically is cast into the word cloud. Where we are moving to is the so-called scientific cloud. It's an environment where the data can be analyzed without you knowing in detail what the computer is, that is, where it is located, that is doing your analysis. And, of course, as you can imagine, we have to store the data for long periods, so we need so-called persistent data storage, one of the other requirements in our business. So we are very much looking forward to the developments that are now emerging over many kinds of sciences in which the scientific cloud is the buzzword of the future, and we want to actually put some flesh onto that idea.
You had, as part of the S3 roadmap, I think for the first time that CERN with the LHC luminosity project was part of that. Why was it? Is that a kind of collaboration?
No, it's a slight change in the philosophy at the European Commission. Before, there was already an S3 roadmap in 2012, I believe, which had the CERN projects included, but at that time the consideration was that the high energy physics group worldwide had evaluated the project and had set its priority. So in fact, the CERN LHC was mentioned in an appendix to that, but now the high luminosity LHC project is gaining so much exposure that it simply needs to be on the roadmap, on the S3 fund. I mean, it's such a prestigious project needs to be mentioned, and this is why it is found its place, not as a future project that needs still go through the approval phases. This one is a so-called landmark, assuming that it simply will be done, which I very much hope so.
If you talk about large computing and large data needs, can you put some numbers on it?
Well, how to put it simply, one number we heard this morning is more than 60% of the traffic that EGI looked at is generated by research scientists. We're speaking here of 500 million cores that are used in this business worldwide. The data storage, we want to preserve the data for a long time. That needs to be provided, so we're talking many hundreds of petabytes, and that will grow unless we learn how to reduce the data volume by more compactification of the data itself.
Thank you very much for this interview.
You're welcome.